Chapter 4: Encoding and Evolution. Everything changes and nothing stands still. Heraclitus of Ephesus, as quoted by Plato in Cratylus, 360 before Christ. Application in inevitable changes over time. Features are added or modified as new products are launched. User requirements become better understood of business circumstances change. In chapter 1, we did introduce the idea of evolvability. We should aim to build systems that make it easy to adapt to change. The evolvability making changes easy on page 21. In most cases, a change to an application feature also requires a change to the data that is stored. Perhaps a new field or record type needs to be captured, or perhaps existing data needs to be present in a new way. The data models we discussed in Chapter 2 have different ways of coping with such changes. Relational databases generally assume that all data in the database conforms to one schema, although that schema can be changed through schema mutations, alter statements. There is exactly one schema in force at any one point in time. By contrast, schema on read, schemaless databases don't enforce a schema, so the database can contain a mixture of older and newer data formats written at different times. See schema flexibility in the documents model on page 39. When a data format or schema change, a corresponding change to the application code often needs to happen. For example, you add a new field to a record and the application code starts reading and writing the field. However, in a large application, code change often cannot happen instantaneously. With server-side application, you may want to perform a rolling upgrade, also known as a staged rollout. Deploying the new version to a few nodes at a time, checking whether the new version is running smoothly and gradually working your way through all the nodes. This allows new versions to be deployed without services downtime, and thus encourage more frequent releases and better evolvability. With client-side application, you are at the mercy of the user. You may not install the updates for some time. This means that old and new version of the code and old and the new data formats may potentially all coexist in a system at the same time. In order for the system to continue running smoothly, we need to maintain compatibility in both directions. Backward compatibility, newer code can read data that was written by older code. Forward compatibility, older code can read data that was written by newer code. Backward compatibility is normally not hard to achieve. As author of the new code, you know the format of the data written by older code, and so you can explicitly handle all, if necessary, by simply keeping the old code to read the old data. Forward compatibility can be trickier because it requires all the code to ignore addition may be made by the newer version of the code. In this chapter, we will look at several formats for encoding data, including JSON, XML, protocol buffers, TRIF, and APRO. In particular, we will look at how they handle schema changes and how they support systems where old and new data and code need to coexist. We will then discuss how those formats are used for data storage and for communication in web services, representational state transfer REST, and remote procedure calls, as well as message passing systems such as actor and message queues. Formats for encoding data. Programs usually work with data in at least two different representations. In memory, that is keeping objects, structure lists, arrays, hash tables, trees, and so on. These data structures are optimized for efficient access and manipulation by the CPU, typically using pointers. When you want to write data to a file or send it over the network, you have to encode it as some kind of self-contained sequence of bytes. For example, a JSON document, since a pointer wouldn't make sense to any other process. This sequence of byte representation looks quite different from the data structure that are normally used in memory. Thus, we need some kind of translation between the two representations. The translation from the in-memory representation to a byte sequence is called encoding, also known as serialization or March-Challen. And the reverse is called decoding, parsing the serialization unmarshalling. Terminology clash. Serialization is unfortunately also used in the context of transactions, see Chapter 7, with a complex different meaning. To avoid overloading the word, we'll stick with encoding in this book, even though serializations is perhaps a more common term. As this is such a common problem, there are myriad different libraries and encoding formats to choose from. Let's do a brief overview. Language-specific formats. Many programming languages come with built-in support for encoding in-memory objects into byte sequence. For example, Java has Java IO serializable, Ruby has Marshall, Python has Pico, and so on. Many third-party libraries also exist, such as Creo for Java. These encoding libraries are very convenient because they allow in-memory objects to be saved and restored with minimal additional code. However, they also have a number of deep problems. The encoding is often tied to a particular programming language, and reading data in another language is very difficult. If you store or transmit data in such an encoding, you are committing yourself to your current programming languages for potentially a very long time, and precluding integrating your system with those of other organizations, which may use different languages. In order to restore data in the same object types, the decoding process needs to be able to instantiate arbitrary classes. This is frequently a source of security problem. If an attacker can get your application to decode an arbitrary byte sequence, they can instantiate arbitrary classes, which in turn often allows them to do terrible things, such as remotely executing arbitrary code. Versioning data is often an afterthought in this library, as they are intended for quick and easy encoding of data. They often neglect the inconvenient problem of forward and backward compatibility. Efficiency, CPU, time taken to encode or decode, and the size of the encode structure is also often an afterthought. For example, Java built-in serializations is notorious for its bad performance and bloat encoding. For these reasons, it's generally a bad idea to use your language built-in encoding for anything other than very transient purpose. JSON, XML, and binary variant. Moving to a standardized encoding that can be written and read by many programming languages, JSON and XML are the obvious contender that I widely know, widely support, and almost as widely dislike. XML is often criticized for being too verbose and unnecessarily complicated. JSON's popularity is mainly due to its built-in support in web browsers, by virtue of being a subset of JavaScript, and simplicity relative to XML. CSV is another popular language-independent format, albeit less powerful. JSON, XML, and CSV are textual formats, and though somewhat human-readable, although the syntax is a popular topic of debate. Besides the superficial syntactic issues, they also have some subtle problems. There is a lot of ambiguity around the encoding of numbers in XML and CSV. You cannot distinguish between a number and a string that happens to consist of digits, except by referring to an external schema. JSON distinguishes strings and numbers, but it doesn't distinguish integer and floating numbers, and it doesn't specify a precision. This is a problem when dealing with large numbers. For example, integers greater than 2 at 53 cannot be exactly represented in an IEEE 754 double precision floating point number. So such numbers become inaccurate when parsed in a language that uses floating point number, such as JavaScript. An example of a number larger than 2 at 53 occurs on Twitter, which uses a 64-bit number to identify each tweet. The JSON returned by Twitter API includes tweets ID twice, once as JSON number and once as a decimal string, to work around the fact that the numbers are not correct parsed by JavaScript applications. JSON and XML have good support for Unicode character string, human-readable text, but they don't support binary strings, sequence of bytes without a character encoding. Binary strings are a useful feature, so people get around this limitation by encoding the binary data as text using base 64. The schema is then used to indicate that the value should be interpreted as base 64 encoded. This worked, but it's somewhat hacky and increased the data size by 33%. There is optional schema support for both XML and JSON. These schema languages are quite powerful and thus quite complicated to learn and implement. Use the XML schema is fairly widespread, but many JSON-based tools don't bother using a schema, since the current interpretation of data, such as number and binary string, depend on information in the schema. Applications that don't use XML JSON schema need to potentially hardcode the appropriate encoding decoding logic instead. CSV does not have any schema, so it is up to the application to define the meaning of each row and column. If an application change, add a new row or column, you have to handle that change manually. CSV is also a quite baggy format. What happens if a value contains a comma or a new line character? Although it is escaping rules have been formally specified. Not all parts implement them correctly. Despite this flaw, JSON, XML, and CSV are good enough for many purposes. It's likely that they will remain popular, especially as the data interchange format for sending data from an organization to another. In this situation, as long as the people agree on what the format is, it often doesn't matter how pretty or efficient the format is. The difficulty of getting different organizations to agree on anything outweighs most other concerns. Binary encoding. For data that is used only internally with your organizations, there is less pressure to use a lowest common denomination encoding format. For example, you could choose a format that is more compact or faster to parse, for example, for a small data set. The gains are negligible, but once you get into the terabytes, the choice of data format can have a big impact. JSON is less verbose than XML, but both still use a lot of space compared to binary format. This observation led to the development of a profusion of binary encoding for JSON. Message pack, BJSON, BJSON, UBJSON, BSON, and SMILE, to name a few. And for XML, WBXML and fast info set, for example. This format has been adopted in various niches, but none of them are widely adopted as the textual version of JSON and XML. Some of these formats extend the set of data types, distinguish integer and floating point number, or adding support for binary strings, but otherwise they keep the JSON XML data model unchanged. In particular, since they don't prescribe a schema, they need to include all the objects field name with the encoded data. That is, in a binary encoding of JSON document, example 4.1, they will need to include the string username, fabric number, and interest somewhere. Let's look at an example of message pack, a binary encoding for JSON. Shows that the byte sequence that you get if you encode the JSON document in example 4.1 with message pack, the first few bytes are as follows. The first byte, 0x83, indicates that what follows is an object. So for top 4 bits equals 0x80 with 3 fields, bottom 4 bits, XX03. In case you are wondering what happens if an object has more than 50 fields, so that the number of fields doesn't fit in 4 bits. If then gets a different type of indicator and the number of fields is encoded in 2 or 4 bytes. The second byte, 0x88, indicates that what follows is a string that is 8 bytes long. The next 8 bytes are the field name username in ASCII. Since the length was indicated previously, there is no need for any marker to tell us where the string ends. The next 7 bytes encoding the 6-letter string value marked with a prefix and so on. The binary encoding is 66 bytes long, which is only a little less than 81 bytes taken by the contextual JSON encoding, with white space removed. All the binary encoding of JSON are similar in this regard. It's not clear whether such a small space reduction and perhaps a speed up in parsing is worth the loss of human readability. In the following sections, we will see how we can do much better and encode the same record in just 32 bytes. Thrift and protocol buffers. Apache Thrift and protocol buffer are binary encoding libraries that are based on the same principle. Protocol buffers was originally developed at Google. Thrift was originally developed at Facebook, and both were made open source in 2007 and 2008. Both Thrift and protocol buffers require a schema for any data that is encoded. To encode the data in example 4.1 in Thrift, you will describe the schema in the Thrift interface definition language. Ideal, like this. The equivalent schema definition for protocol buffer looks very similar. Thrift and protocol buffer each come with a code generation tool that takes a schema definition like the ones shown here and produce classes that implement the schema in various programming languages. Your application code can call this generated code to encode or decode record of the schema. What does data encoded with this schema look like? Confusingly, Thrift has two different binary encoding formats, called binary protocol and compact protocol, respectively. Let's look at binary protocol first. Encoding example 4.1 in that format takes 59 bytes as shown in. Similar to figure 4.1, each field has a type annotation to indicate whether it is a string, integer, list, and will require length indication, length of the string, number of items in the list. The string that appears in the data, Martin Day string hacking, are also encoded as ASCII or rather UTF-8, similar to before. The big difference compared to figure 4.1 is that there are no field names, username, map, favorite, number, interest. Instead, the encode data contain field tags, which are number 1, 2, and 3. Those are the numbers that appear in the schema definition. Field tags are like alias for fields. They are a compact way of saying what fields we're talking about without having to spell out the field's name. The thrift compact protocol encoding is semantically equivalent to binary protocols, but as you can see in figure 4.3, it packs the same information into only 34 bytes. It does this by packing the field type and tag number into a single byte, and by using variable length integer, rather than using a full hey byte for the number 1337. It is encoded in 2 bytes, with the top bit of each byte used to indicate whether there are still more bytes to come. This means numbers between 64 less 64 and 63 are encoded in 1 byte. Numbers between less 81, negative 8192 and 8191 are encoded in 2 bytes, etc. Bigger numbers use more bytes. Finally, protocol buffers, which has only one binary encoding format, encodes the same data as shown in figure 4.4. It does the bit package slightly different, but it's otherwise very similar to Thrift compact protocol. Protocol buffer fits the same record in 33 bytes. One detail to know, in the schema shown earlier, each field was marked either required or optional, but this makes no difference to how the field is encoded. Nothing in the binary data indicates where the fields were required. The difference is simply that requires enable a runtime check that fails if the field is not set, which can be useful for catching bugs. Field tags and schema evolution. We said previously that schema inevitable needs to change over time. We call this schema evolution. How do Thrift and protocol buffers handle schema change while keeping backward and forward compatibility? As you can see from the example, an encode record is just the concatenation of its encoded fields. Each field is identified by its tag number, the number 1, 2, 3 in the sample schema, and annotated with a data type. If a field value is not set, it's simply omitted from the encode record. From this, you can see that field tags are critically to the meaning of the encoded data. You can change the name of the field in the schema since the encoded data never refers to a field name, but you cannot change a field tag since that would make all existing encoded data invalid. You can add new fields to the schema, provided that you give each field a new tag number. If all code which doesn't know about the new tag number you add tries to read data written by new code, including a new field with a tag number it doesn't recognize, it can simply ignore that field. The data type annotation allows the parser to determine how many bytes it needs to skip. This maintains forward compatibility. All code can read records that were written by the new code. What about backward compatibility? As long as each field has a unique tag number, new code can always read all data because the tag numbers still have the same meaning. The only deal is that if you add a new field, you cannot make it required. If you were to add a field and make it required, that check will fail if new code read data written by old code, because the old code will not have written the new field that you add. Therefore, to maintain backward compatibility, every field you add after the initial deployment of the schema must be optional or have a default value. Removing a field is just like adding a field with backward and forward compatibility concerns reserved. That means that you can only remove a field that is optional. A required field can never be removed, and you can never use the same tag number again because you may still have data written somewhere that includes the old tag number, and that field must be ignored by new code. Data types and schema evolution. What about changing the data type of a field? That may be possible. Check the documentation for details, but there is a risk that value will lose precision or get truncated. For example, say you change a 32-bit integer into a 64-bit integer. New code can easily read data written by old code because the parse can fill in any missing bits with zeros. However, if old code reads data written by new code, the old code is still using 32 bits variable to hold the value. If the decode 64 bits value won't fit in 32 bits, it will be truncated. A curious detail about protocol buffers is that it does not have a list of arise data types, but instead have a repeating marker for fields, which is a third option alongside required and optional. As you can see in figure 4.4, the encoding of the repeated field is just what it says on the theme. Same field tags simply appears multiple times in the record. This has the niche effect that it's okay to change an optional single value field into a repeated multi-value field. New code reading all data sees the list with 0 or 1 element, depending on whether the fields was present. Old code reading new data sees only the last element of the list. Brief has a dedicated list data type, which is parameterized with the data type of the list elements. This does not allow the same evolution with single value to multi-valued as protocol buffer does, but it has the advantages of supported nested lists. Avro. Apache Avro is another binary encoding format is interesting different from protocol buffer and Thrift. It was started in 2009 as a subproject of Hadoop as a result of Thrift not being a good fit for Hadoop use cases. Avro also uses schema to specify the structured data being encoded. It has two schema languages, one Avro IDL intended for human editing and one based on JSON that is more easily machine readable. Our example schema written in Avro IDL might look like this. The equivalent JSON representation of that schema is as follows. First of all, notice that there are no tag numbers in the schema. If we encode our example records, example 4.1, using this schema, the average binary encoding is just 32 bytes long. The most compact of all the encoding we have seen. The breakdown of the encoding byte sequence is shown in figure 4.5. If you examine the byte sequence, you can see that there is nothing to identify fields or the data types. The encoding simplified consists of values concatenated together. A string is just a length prefix followed by UTF-8 bytes, but there is nothing in the encoded data that tells you that it is a string. It could just as well be an integer or something else entirely. An integer is encoded using a variable length encoding, the same as Thrift compact protocol. To parse the data, the binary data, you go through the fields in the order that they appear in the schema and use the schema to tell you the data type of each field. This means that the binary data can only be decoded correctly if the code reading the data is using the exact same schema as the code that wrote the data. Any mismatch in the schema between the readers and the writers will mean incorrectly decoded data. So, how does Avro support schema evolution? the writer's schema and the reader's schema. With Avro, when an application wants to encode some data, to write it to a file or a database, to send it over to a network, etc., it's encoded data using whatever version of the schema it knows about. For example, that schema may be compiled into the application. This is known as reading writer's schema. When an application wants to decode some data, read it from a file or a database, receive it from a network, it is expecting the data to be in some schema, which is known as the reader schema. That is the schema the application code is relying on. Code may have been generated from the schema during the application build process. The key idea with Apro is that the writer's schema and the reader's schema don't have to be the same. They only need to be compatible. When data is the code read, the Avro library resolves the difference by looking at the writer's schema and the reader's schema side by side and translating the data from the writer's schema into the reader's schema. The Avro specification defines exactly how this resolution works, and it's illustrated in figure 4.6. For example, it's not a problem if the writer's schema and the reader's schema have their fields in a different order because the schema resolution matches up the fields by field name. If the code reading the data encounter a field that appears in the writer's schema but not in the reader's schema, it is ignored. If the code reading the data expects some field, but the writer's schema does not contain field of the name, it is filled in with a default value declared with the reader's schema. Schema evolution rules. With Avro, forward compatibility means that you can have a new version of the schema as writer and an old version of the schema as readers. Conversely, backward compatibility means that you can have a new version of the schema as reader and an old version as writer. To maintain compatibility, you may only add or remove a field that has a default value. The field favorite number in our Avro schema has a default value of null. For example, say you add a field with a default value, so this new field exists in the new schema but not the old one. When a reader using the new schema reads records reading with the old schema, the default value is filled in for the missing field. If you were to add a field that has no default value, new readers won't be able to read data written by all writers, so you will break backward compatibility. If you were to remove a field that has no default value, all readers wouldn't be able to read data written by new writers, so you would break forward compatibility. In some programming languages, null is an acceptable default for any variable, but this is not the case in Avro. If you want to allow a field to be null, you have to use a union type. For example, union null long string field indicate that fields can be a number or a string or a null. You can also use a null as default value if it is one of the branches of the union. This is a little more verbose than having everything nullable by default, but it helps prevent bugs by being explicit about what and can not be null. Consequently, Avro doesn't have optionals and require marker in the same way as protocol buffer and thread do. It has union type and default values instead. Changing the data type of the field is possible, provided that Avro can convert the type. Changing the name of the field it is possible but a little tricky. The reader's schema can contain aliases for field name, so it can match an old writer schema field name against the aliases. This means that changing the field name is backward compatible, but not forward compatible. Similarly, adding a branch to a union type is backward compatible, but not forward compatible. But what is the writer schema? That is an important question that we have closed over so far. How does the reader know the writer schema which a particular piece of data was encoded? We can just include the entire schema with every record, because the schema will likely be much bigger than the encoded data, making all the space saving from the binary encoded futile. The answer depends on the context in which Avro is being used. To give a few examples, large files with lots of records. A common use for Avro, especially in the context of Hadoop, is for storing a large file containing millions of records, or encoded with the same schema. We will discuss this kind of situation in chapter 10. In this case, the writer of the file can just include the writer's schema once. at the beginning of the file. Avro specifies a file format, object container files to do this. Databases with individual written records. In a database, different records may be written at different point in time using different writer schemas. You can assume that all the records will have this same schema. The simple solution is to include a version number at the beginning of every encoded record and to keep a list of the schema version in a base. A reader can fetch a record, extract the version number, and then fetch the writer schema for that version number from the database. Using that writer schema, it can decode the rest of the record. Work this way, for example, sending record over a network connection. When two processes are communicating over a bidirectional network connection, they can negotiate the schema version and connection setup and then use that schema for the lifetime of the connection. The average RPC protocol, see data flow through service, REST, and the RPC on page 131 work like this. A database of a schema version is useful thing to have in any case, since it acts as documentation and gives you a chance to check schema compatibility. As the version number, you could use a simple increment integer or you could use a hash of the schema. Dynamically generated schemas. One advantage of Avro's approach compared to protocol buffers and Thrift is that the schema doesn't contain any tag number. But why it is important? What the problem with keeping a copy of number in the schema? The difference is that Avro is friendly to dynamically generated schemas. For example, say you have a relational database whose content you want to dump to a file, and you want to use a binary format to avoid the aforementioned problem with contextual format, JSON, CSV, SQL. If you use Avro, you can fairly easily generate an Avro schema in the JSON representation we saw earlier from the relational schema and encode the database content using that schema, dumping it all to an Avro object container file. You generate a record schema for each database table, and each column becomes a field in that record. The column name in the database map to the field name in Avro. Now, if the database schema change, for example, a table has one column add and one column remove. You can just generate a new Avro schema from the data database schema and export data in the new Avro schema. The data export process does not need to pay any attention to the schema change. It can simply do the schema conversion every time it runs. Anyone who reads the new data files will see that the fields of the record have changed, but since the fields are identified by name, the updated writer schema can still be matched up with the old reader schema. By contrast, if you were using Thrift or protocol buffer for this purpose, the field tag would likely have to be assigned by hand. Every time the database schema changes, an administrator will have to manually update the mapping from the database column names to field tag. It might be possible to automate this, but the schema generator will have to be very careful to not assign previously used field tags. This kind of dynamically generated schema simply wasn't a design goal of Thrift or protocol buffer where it was for Avro. Code generation and dynamically typed languages. Thrift and protocol buffer relies on code generation. After the schema has been defined, you can generate code that implements this schema in a programming language of your choice. This is useful in statically typed languages such as Java, C++, or C# because it allows efficient in-memory structures to be used for the code data, and it allows type checking and auto-completion in IDEs when writing programs that access the data structure. In dynamically typed programming languages such as JavaScript, Ruby, or Python, there is not much point in generating code. Since there is no compile time, type checker to satisfy, code generation is often frowned upon in these languages, since They otherwise avoid an explicit compilation step. Moreover, in the case of dynamically generated schema, such as Avro schema generated from a database table, code generation is an unnecessary obstacle to getting to the data. Avro provides optional code generation for statically typed programming languages, but it can be used just as well without any code generation. If you have an object container file which embeds the right schema, you can simply open its generated schema, such as Avro schema generated from a database table. Code generation is an unnecessary obstacle to get into the data. Avro provides optional code generation for statical type programming languages, but it can be used just as well without any code generation. If you have an object container file which embeds the writer schema, you can simply open it using Avro library and look at the data in the same way as you could look at a JSON file. The file is self-describing since it includes all necessary metadata. This property is especially useful in conjunction with dynamically property with dynamically typed data processing languages like Apache Pig. In Pig, you can just open some arrow files, start analyzing them, and write derived data set to output files in Avro format without even thinking about schemas. The merit of schemas. As we saw, protocol buffers, thrift, and arrow all use a schema to describe a binary encoded format. The schema language are much simpler than XML schema or JSON schema, which support much more detailed validation rules. The string value of this field must match this regular expression, or the integer value of this field must be between 0 and 100. As protocol buffer, thrift, and arrow are simpler to implement and simpler to use, they have grown to support a fairly wide range of programming languages. The idea on which these encoding are based are by no means new. For example, they have a lot of in common with ASN.1, a schema definition language that was first standardized in 1984. It was used to define various network protocols and its binary code encoding DIR. It's still used to encode SSL certificates, X.509. For example, ISN.1 supports schema evolution using tag numbers, similar to protocol buffers and thrift. However, it's also very complex and badly documented. So ASN.1 is probably not a good choice for new applications. Many data systems are also implement some kind of proprietary binary encoding for their data. For example, most relational databases have a network protocol encoding for their data. For example, most relational databases have a network protocol over which you can send queries to the database and get back responses. Those protocols are generally specific to a particular database, and the database vendor provides a driver using the ODBC or GDBC APIs that decodes responses from the database network protocol into any memory data structure. So we can see that although textual data formats such as JSON, XML, and CSV are widespread, binary encoding based on a schema are also a viable option. They have a number of nice properties. They can be much more compact than various binary JSON variants since they can omit fields named from the encoded data. The schema is a valuable form of documentation, and because the schema is required for decoding, you can be sure that it is up to date, whereas manually maintained documentation may easily diverge from reality. Keeping a database of schema allows you to check forward and backward compatibility of schema change before anything is deployed. For usual users of statically typed programming languages, the ability to generate code from the schema is useful since it enables type checking at compile time. In summary, check schema's evolution allows the same kind of flexibility as schema-less schema on read JSON database provide. See schema flexibility in the documented model on page 39, while also providing better guarantees about your data and better to live.